All right, today we're going to do ethers and sulfides. Like I said, this is a chapter that doesn't have a whole lot of content. There are some reactions that are interesting. In general, ethers don't do much in the way of chemical reactions. This is a neat guy. We'll talk about it a little bit later. 18 Crown 6 it's called. It actually chelates very specifically a potassium ion. This is just a list here of common ethers, just to give you a feel. An ether basically has alkyl or aryl groups on either side of an oxygen. The oxygen, of course, has lone pairs, but there's no hydrogen, etc. Because of that, ethers are fairly inert in terms of their chemical reactions. This is diethyl ether. Diethyl ether is what we used to use, or someone used to use years ago for anesthesia, etc. Phenolmethyl ether, tetrahydrofuran, a very common cyclic ether. This is ethylene oxide. It's an epoxide, and probably the most interesting reactions of ethers are going to involve epoxides like this. This is a very important reactant industrially, ethylene oxide. When you name an ether, as you can tell by the slide here, essentially you want to name the groups on either side in terms of priorities. Ethers are very low priority. They're treated as a substituent on an alkane, for example, just like a chlorine or something like that. If it's a substituent on somebody else's chain, you simply call it an alkoxy substituent. So this would be ethoxy, whatever. If it's a simple ether like this, we use ether. Oxiranes or epoxides are slightly different. And again, a lot of the ethers have common names that are very widely used. Let's go ahead and look at some simple ethers here, and let's do some nomenclature. When you look at something like our first example, we see we have an ether, and we have alkyl groups on both sides, right? What you have to do is decide who is going to be the parent. The parent is going to have the most carbons, or it's going to be the most complex. So, we look at this, we have a 4-carbon chain here, we have a 3-carbon chain here. 2-methylpropane, 4-carbon chain, is going to be the parent, simply because it has the most carbons. So, we're going to do this as our parent, and this is going to be carbon 1 on our parent chain. Now, our parent chain has a methyl group in carbon 2, so it's a 2-methyl substituent, 2-methylpropane. Our side chain here, if this was just a chlorine, we would call it a chloro, right? Remember, it's an alkoxy here, so we'll call this a propoxy. Now we take it and we string it all together. We have a 2-methylpropane parent, and we have a 1-propoxy substituent. 2-methyl, 1-propoxy propane. Working backwards, 2-methylpropane is our parent, that's this guy. 1-propoxy, as this guy, is a substituent. Now our next one here, we have symmetry, don't we? So, there's no competition as to who's going to be parent, is there? Let's just go ahead and let this side be our parent chain. They're identical. So just like over here, we're going to have a 2-methylpropane as our parent. We have to name this guy. Now it's going to be a propoxy again. But because we have the methyl out here, this is going to be a 2-methylpropoxy substituent. Now we take these and string them all together.
Why wouldn't you go from the other side?
Well, you could. They're identical. 2-methyl. Well, again, our parent here, starting with our parent, 2-methylpropane. Right? That's our parent. Attached to carbon 1 of our parent, we have a 2-methylpropoxy substituent. Again, over here, our parent is 2-methylpropane with a propoxy in carbon 1. Now our next guy, we have 3 carbons on both sides, but this has a chlorine, so that makes it more complex, doesn't it? So that means this side is going to be our parent, and that will be carbon 1. This is going to be a 2-chloropropane parent. And what's our substituent going to be? Just like up top, 3-carbon chain here, so it's going to be a 1-propoxy. Putting it all together, we're going to go 2-chloropropane as our parent with a 1-propoxy substituent. 2-chloro, 1-propoxy propane. And finally here, now we have 4 carbons on this side, so that's going to be parent. Only 3 on this side, so our parent here is going to be a 2-methylpropane parent. Our substituent here is going to be a propoxy, except it has a chlorine in carbon 2. So this is going to be a 2-chloropropoxy substituent. Go ahead and quickly write the name. Well, just like up here, we're going to have a 2-methylpropane as our parent, and our substituent here is going to be a 1-chloropropoxy. 1,2-chloropropoxy, 2-methylpropane.
Yes, please.
Any questions? Now, nomenclature of ethers isn't something we're going to spend any time on, really. I'm sorry?
I have a question. How come in the second one and the fourth one, the second one you broke up methylpropane and then the last one you didn't split up methylpropane?
The parent here is a propoxy, so alphabetically I think the
Oh,
methyl comes first. So. No, we're not gonna do much. Remember, we're gonna have tons and tons of real chemistry to do. Ether nomenclature is, again, just like ethers, not very important, not something we're gonna talk about. Mostly we're going to be able to just name them as things like diethyl ether or phenylmethyl ether, etc. All right, let's just talk about them a little bit. Just like in alcohols and in water, the oxygen is essentially tetrahedral. It's sp3 hybridized, of course. Remember, we have a dihedral angle of about 112. In a perfect tetrahedron, it would be 109.5. This is opened up a little bit because of the bulk of the groups attached on both sides. Remember, we have two lone pairs, and any chemistry that happens in the ether on the oxygen is really just going to be the ether oxygen functioning as an electron donor, that is a Lewis base. So essentially sp cubed brings this open a little bit depending upon the size of what's attached, whatever. If we want to make ethers industrially, the one that is typically made is going to be diethyl ether, used a lot as a solvent, etc. We can make it on a large scale from ethanol, sulfuric acid. Mechanism involves protonation of 1 mole of ethanol, attacked by a second, lose water, and we make diethyl ether. Now, we've used diethyl ether in the lab. Diethyl ether itself is very low boiling. It doesn't undergo internal hydrogen bonding, so its boiling point is about 35 degrees centigrade. Very, very volatile, and it's also very explosive. It burns very rapidly. We have to be very careful when we use it. Also have to be very careful with ether, because if you have an old container of ether, something that you've opened, and used some, then closed it back up, ether can undergo a free radical reaction with oxygen. What happens is oxygen will react with the ether. We form this radical. Now this radical, of course, is resonance stabilized next to an oxygen, so it's fairly stable. It then reacts with another mole of oxygen, and we form what's known as a hydroperoxide. Hydroperoxides are very explosive compounds. So we have something that is very, very volatile, that's very, very flammable, and in the presence of oxygen, forms an explosive byproduct. So you do have to be very careful whenever you use diethyl ether. Make sure the can is fresh. Don't let it sit open. Once it starts getting down towards the bottom, you're better off just letting it go away. All right. The simplest way to make an ether in the laboratory is a reaction that's known as the Williamson ether synthesis. Now, if you take a standardized exam of some sort, you'll probably see this reaction listed by name. So Williamson really did well for himself, but it's a very, very simple reaction. It's just an SN2. To make an ether with the Williamson synthesis, all you do is take an alkoxide, an alkyl halide of some sort, simple displacement, bromine leaves, and we make the ether. Reaction goes essentially quantitatively with simple primary alkyl halides. Very nice, very happy reaction. Let's go ahead and do some simple examples. Go ahead and draw the products of these Williamson synthesis ethers. Remember, all that's going to happen is the oxide is going to attack. We're going to displace our leaving group, and we will make our ether. In a reaction like this, we typically use something like sodium amide to make the anion. So we're dealing with the alkoxide anion directly. And again, that's one reason the thing goes so well and so easily. Oxygen attacks, bromine leaves, and we wind up with benzyl methyl ether. Over here, phenoxide, very nice nucleophile. The oxyanion will attack, bromine will leave. We will get the benzene ring on one side and the cyclopentane CH2 on the other. Finally, here we have this as a nucleophile, tosylate. Now remember we talked about when we did alcohols. If you want to make the alcohol a better leaving group, in order to do something like an SN2 reaction, one of the ways you can do it is to convert it to a toluene sulfonate ester. Do this just with toluene sulfonyl chloride, very simple reaction. This is abbreviated typically in organic chemistry as OTS. So this just stands for a very good leaving group here, just like halogen. Again, the oxygen will attack, tosylate will leave, and we simply make the ether. Any questions? Williamson ether synthesis couldn't be simpler.
So those bromines are gonna leave because it's, am I using the right terminology?
I'm sorry, what?
Those bromines are always gonna leave? 'Cause it's
The bromine, yes. Remember when you have an SN2 reaction, you have a nucleophile, that's this. You have an electrophilic carbon, so that's a partially positive carbon. That will be CH2, and you have a leaving group. So nucleophile, electrophile, leaving group. Nucleophile, electrophile, leaving group. You can also make an ether using the same approach that we use to make Markovnikov alcohols with mercuric acetate. If you recall, with mercuric acetate, we would take an alkene, react it first with mercuric acetate in water. That would give us a mercuridium ion. Second step, attack by water. And finally, sodium borohydride to get rid of the mercury. Well, if we do this in the presence of not water, but an alcohol, in this case methanol, we simply get attacked by methanol instead of water. So instead of an alcohol, we get a simple ether. Just like the reaction of the alkene up top, we're going to have Markovnikov regiochemistry, and because we have a mercuridium ion, we do not have rearrangements. Now this reaction goes all the way back to chapter 6 or 7, in case you've forgotten the mechanism. Step 1, we form our mercuridium ion. That's why we don't have rearrangements. It's not a carbocation. It's a bridged mercuridium ion. Step 2, the nucleophile, in this case methoxide, is going to attack. It's going to attack at the carbon that would give the most stable carbocation. That's why we get Markovnikov regiochemistry. So methoxide attacks, we get our ether. And finally, in our second step, we have to get rid of our mercury. That's what sodium borohydride does. Nice, simple reaction. Now, perhaps the most useful of all the ethers are epoxides. Epoxide is also properly referred to as an oxirane. Oxirane means three-membered ring with an oxygen. Can be formed from an alkene in the presence of an organic peracid. Peracid, simply a carboxylic acid with too many oxygens. Mechanism, you simply take the extra oxygen here and insert it into the pi system. Very simple reaction. Once we have the epoxide, we'll see the epoxide is very, very versatile because it can undergo lots and lots and lots of simple reactions. When you see this written, you'll either see as a reaction. You'll either simply see the word peracid, and you know that you're making an epoxide. Sometimes you will see it written out this way, say a methyl group here, COOH. Again, that's a peracid. There's a very nice reagent that works very well, and this is magnesium monoperphthalate. This is abbreviated MMPP, and these days this is probably the reagent of choice. Very nice, very stable, very easy to work with. Magnesium monoperphthalate, again here's our peracid, MMPP. So that's really the conditions you would see over the arrow here, simply MMPP. We can also make an epoxide using an internal SN2 reaction. Now again, remember back in chapter 6-ish, we took an alkene and we reacted it with HOBr. When we did that, we formed a halohydrin. Now the mechanism involved formation of a bromonium ion, then attacked by hydroxide. That means we have trans stereochemistry here. We also have regioselectivity of the hydroxyl group is bonded to the carbon that would give the most stable carbocation. So it's Markovnikov relative to the hydroxyl group. Okay, so this is a reaction again from chapter 6. Well, if you think about the Williamson ether synthesis, what we did was simply take an alkoxide and we took an alkyl halide, right? Well, look at this molecule. If we took this and treated it with sodium amide or something, we would make the alkoxide, wouldn't we? Right here, we have a leaving group. So all that happens here is the alkoxide attacks, bromine leaves, and we make the epoxide. Very nice, simple reaction. Reaction with HOBr typically goes very nicely. So in terms of peroxides, we have two ways to do it. Epoxides, we have two ways we can make them. One is with peracids, and one is with this internal SN2 reaction. Any questions? All right, let's go ahead and make some epoxides. Remember, MMPP stands for magnesium monoperthalate. It is simply a code word for a peracid. So here above the arrow, again, you could see the structure of a peracid written. You could just see the word peracid, or you could see something like MMPP. All in the world that happens is that the peracid oxygen is inserted into the double bond here, and we make the epoxide. This is styrene, and this is styrene oxide. I'm sure that everybody these days has something somewhere that's held together with epoxy resin, isn't it? Don't you? Everything breaks, take a little bit of epoxy, dibby-dab it together. This is epoxy resin. And what you do is you make a polymer by a ring opening on the epoxy ring. Again, we're going to take our double bond here, simply add the peroxy oxygen to the pi system. And finally, this is a two-step reaction. Step one, we're going to add HOBr. Remember, the reaction is Markovnikov relative to the hydroxyl group. So our intermediate here, this would be a secondary carbocation, that would be tertiary. So the hydroxyl group will add here. When we treat it with base, we get an alkoxide, bromine leaves, and we make the epoxide. Any questions?
So where is that, sorry,
No,
do you have a question?
oh, I can.
Where does that bond go right here? On the
Which one?
The last reaction?
This guy?
Yes,
Well, this is our alkene.
okay,
The oxygen is simply going to be inserted right here on the alkene pi system.
okay.
So here, this is the oxygen. Simply inserted on top of it. Step one again, we make the halohydrin. Markovnikov regiochemistry relative to the hydroxyl group. Then the internal SN2 reaction to give the product.
Because bromine's gonna leave.
Yep.
These two.
Going back here, electrophilic carbon, nucleophile, leaving group. Three things to think about always in an SN2 reaction. All right, the next thing we talk about, of course, is going to be reactions of, we've talked about how to make them. What do they do? Well, they don't do much. They just really don't. About the best thing you can do here is to do the reverse of the Williamson ether synthesis. So this is the unsynthesis, if you will. If you have a nice simple ether here, like a methyl group, it has to be a primary carbon really. We can actually split the ether and go backwards. If we take something like HI, hydroiodic acid, have to heat it up, so this is like at reflux. What happens is the iodide, as a nucleophile, will simply attack the methyl group. Step one, we're going to protonate the ether. Remember, it does have those. And that makes this a decent leaving group, doesn't it? Step two, iodide attacks, and we wind up with the alcohol and the alkyl iodide. So this here is just the opposite of the Williamson ether synthesis. All we're doing is splitting it open. Iodide is the one that works best because it is such a good nucleophile. And that is just about the only real reaction of ethers we're going to talk about. Isn't that refreshing? Now when I say ethers, I'm talking about ethers and not epoxides. Because unlike regular ethers, epoxides are interesting. They do undergo lots of reactions. We're going to look at half a dozen, and our set looks something like this. If we start off with an epoxide, and we're going to go over these one by one. So this is just an overview. Start off with an epoxide. We put it in fairly strong acid in water. What we'll do is we will ring open here. Water will be our nucleophile, and we will make a 1,2 diol. Now way back in chapter 6 again, we learned how to make 1,2 diols, didn't we? Out of alkenes. We did that with permanganate or osmium tetroxide. The stereochemistry there was cis, because both oxygens came from permanganate, same side. Here, we're going to see we have a trans 1,2 diol. So this is kind of neat. We now know how to make cis 1,2 diols from chapter 6 and trans 1,2 diols. We'll do a problem based on that in just a bit. Well, nonetheless, the addition product, it depends on what you have attached. I mean, if this was in a ring, for example, you would know cis and trans for sure. If we have HX instead of just like sulfuric acid, instead of water being our nucleophile, halogen will, and we go back to our halohydrin. So the reverse of the reaction we just saw. Alkoxide, slightly different mechanism. Hello, George.
Good morning.
Slightly different mechanism here. Alkoxide attacks as a nucleophile. This is going to hit this carbon, ring open, and we're going to make it ether alcohol. Just like alkoxide can attack here, we can also do this with a Grignard. Remember, a Grignard is a glorified carbanion. It can add here, ring open. And finally, lithium aluminum hydride, the same thing. H minus is our nucleophile. So we're going to put a hydrogen on here and just wind up with an alcohol. So we're going to go through all of these one by one. The refreshing thing is that these all go by essentially the same mechanism. So it's very easy to remember. All we're really doing is opening the epoxy ring and adding a substituent. So let's go ahead and get started with the simple acid hydrolysis. If we take an epoxide and we stick it in acidic conditions, what's going to happen, the only thing that can happen, is that the oxygen will function as a Lewis base and accept a proton. So step one, we're going to protonate this thing. And once we've done that, this hydroxyl group is a really, really good leaving group. That makes one of these carbons very electrophilic. So we have an electrophilic carbon and a leaving group, all set up for an SN2 reaction, right? The SN2 reaction, water attacks, breaks our bond here, simple SN2, and we wind up with the trans 1,2 diol. Why is it trans? Because it's SN2. This comes in the backside, So this is on the opposite face. They're anterofacial. This is going to be our standard mechanism for ring opening of an epoxide. Nucleophile comes in backside, kicks out the oxygen as a ligand group. Attack by HX, going to be exactly the same thing. Remember, X can be chlorine, bromine, or iodine. We're going to protonate, form exactly the same intermediate. Only difference is our nucleophile here is going to be the halogen anion. Halogen anion will attack. Again, it's backside, SN2, and we remake our halohydrin. In the presence of a strong base, we'd make alkoxide, and it would go backwards, wouldn't it? So exactly the same reaction. Any questions? Now, when you do an acid-catalyzed ring opening, this is how you do it. Step 1 is going to always be protonation. Step 2, attack. We can also open the ring with a very strong nucleophile. We're going to look at 3 nucleophiles. Start off with something like alkoxides. So if we take an alcohol and convert it into the stable alkoxide, it is a very strong, very stable nucleophile, isn't it? Lots of electrons. Because this is a strained ring, we can knock this ring open if we have a good, healthy nucleophile. The reaction looks like this. Alkoxide attacks, ring opens. We start with an alkoxide and we wind up with an alkoxide. So energetically, we're even. We're breaking even here. Our second step is always to take this mixture, acidify it, and we wind up with the alcohol. So what we've done here is simply add alkoxide beta to the carbon, I guess this is alpha, to the carbon bearing the hydroxyl group.
What's that first step? What's that swimming in? The first one.
This guy,
Yeah, what's it swimming in?
this, let's say we were using ethoxide here. We would do ethoxide and ethanol. So alkoxide, ethoxide, whatever, attacks, ring opens. Remember, this ring is strained. These angles want to be 112, don't they? And they're 60. So there's a lot of ring strain here. This thing wants to pop open. Give it a good kick in the behind with a good nucleophile, and it just boing, springs open. Instead of alkoxide, we can do this with our friend, the Grignard reagent. Now we have to do this in ether. That is a Grignard reagent. But again, all that's going to happen is the carbanion portion of the Grignard going to attack. A ring is going to bounce open. We'll make the intermediate alkoxide, which we can acidify to make the alcohol. So this is another way to make alcohols. Once again, this is very versatile, isn't it? Let's say that we were dealing here with ethylene oxide. So these are all hydrogens. What we've done is take our Grignard carbon, we've added 2 carbons to it, and made an alcohol. we can add 2 carbons all at once. Here's our bond. This guy used to be the oxyrain and is now an alcohol.
What was the oxygen again?
These carbons here
Yes.
used to be the epoxide or oxyrain. The stuff in blue here is what we've added. The Grignard reagent and the hydrogen from the workup. Finally, just like we can add R minus, that is the Grignard, we can also add H minus from lithium aluminum hydride. Reaction is exactly the same. H minus is going to attack, ring is going to open. We form the alkoxide, work it up with aqueous acid, and we've made the alcohol. So think about it, we make the epoxide from an alkene, don't we? So if we started off with an alkene, simply convert it to the epoxide, reduce it with lithium aluminum hydride, and we've made an alcohol. Nice, simple, synthetic method. Any questions? Well, let's do a few then. We look at our first one, we say we have styrene oxide, a simple epoxide. We have a Grignard reagent. Now, we all know this carbon on the isopropyl group is going to be the anion, right? That's our nucleophile. This is an SN2 ring opening. Remember, SN2 reactions are very sensitive to steric bulk. So the attack is always at the least hindered carbon, isn't it? Because it has to get in there. So that means our anion is going to add here on the end. Just a nice, easy place to get in. So when you draw the product, we're going to make an alcohol, aren't we? Alcohol, this is going to be an OH. On one side, we will have a benzene ring. This carbon is going to be attached to our Grignard reagent. So this is going to be a CH2 and then our isopropyl. If you haven't drawn it, go ahead and try. Benzene ring, CHOH, CH2, isopropyl. Here's our CHOH, benzene ring, CH2, that's this guy, and the isopropyl. Just put the pieces together. All right, our next one, we have an epoxide and we have aqueous acid. So what's going to happen here? Step one, we're going to protonate the oxygen, aren't we? Step two, we're going to do an SN2 attack. we're going to wind up with a 1,2 diol, and they're going to be trans. So when you draw the product here, we're going to have a 6-membered ring. On one carbon, we're going to have a methyl group and an OH. On the other carbon, we'll have another OH, but they must be trans to each other. So remember how you would draw that. In a 6-membered ring, if the 2 OHs are going to be trans, they will either be both equatorial or both axial. If they're both equatorial, we have 2 equatorials, 1 axial substituent. This is probably a bit more stable than the other option. Again, equatorial, equatorial, these are trans. One's up, one's down. We made the trans 1,2 diol.
See, Dr. Young, just so I can be clear, you're telling me that even when they're both on the equatorial, that one could, on an equatorial plane, one could be facing up and one could be facing down.
Right. Remember what a 6-member ring looks like. A
Oh,
6-member
because it
ring.
became a bolt and then a flip and everything?
That's right. So we have, think about our ring plane here. Again, this is pointing up from the ring plane. This is pointing down from the ring plane. Up and down, they are axial or trans.
How would I visualize this for this one? Because I would have drawn a ring. How would I visualize that that's supposed to be a chair that I start out with? When
Well, I don't have
finish
a
the
model of this. I suppose you could go back to chapter 3, look at the recording that's on YouTube, where we talk about cycloalkanes and clearly define axial, equatorial, trans,
That's
etc.
chapter 5 is on there right now.
Yeah.
That's how I'm reviewing right now.
Right
I
now,
would
what
draw
you would
this
do is
flat, so
you would
I-
just look and say, again, our ring plane here, here's our ring plane. It's puckered and it's flipping, right? We know that, we remember that. But if we had a static ring plane, this is pointing down from it and this is pointing up from it.
That I get.
That's trans.
That I get. What I don't get is that I would, as a student, draw this a flat way, as you refer to your
Oh, well, you,
recordings. Why would I? How would I go about it, like thinking this way, as far as strategy of this reaction?
well, okay, if this was an exam question,
Yes.
if I simply said, draw the product,
Mm-hmm.
you could draw this. That would be perfectly correct. You could draw it with both hydroxyl groups axial. That would be perfectly correct. Or you could draw a flat 6-membered ring and use little wedges to show one OH back, one OH forward.
Because that's how I was going to draw it, a flat way with the
Yeah.
wedges.
Okay, with wedges, that'll work.
Okay.
If, however, I had said, draw this in its most stable chair conformation, then you would have to draw this here.
Okay.
Yeah.
Again, just, I hope I didn't forget what thought was. So, when I'm looking at this right now, it's not finished yet. If I flip the forward down, it'll make the OH and axial, and that's where I'll get in my mind, how an axial and equatorial equals a trans.
All right, if you, again, did a ring inversion, so you flip this down, flip this up, these equatorial groups would become axial.
Oh, both?
So one up, one down, straight up, straight down, and that would be clearly trans. When the reaction first happens, you form the diaxial, and then it goes to the more stable diaquatorial.
But with that being trans and then it's opposite, it's axial, so then that's not the most stable. The
Right.
most stable is equatorial, so
Right.
that's why this would be the answer.
That's why this is the most stable isomer.
Okay.
See how you have to remember everything from
No, it's true.
organic one?
Connects.
Of course you do. All right, and our last one here, we're simply taking an alkoxide and we're doing an SN2 ring opening, followed by acid workup. Because it's SN2, we're going to attack the least hindered carbon, which is going to be the CH2 here, right? So what's our product going to look like? The ethoxide is going to be attached here. So this will be a CH2 with the ethoxide dangling down. This carbon will have an OH and 2 methyls. This is our CH2 here. There was this one over here, same CH2. Ethoxide is attached. This carbon has an OH and 2 methyls. Yeah.
Alright, so when you look at the first problem and the second problem, in the finished product, we have 2 OHs. In the second problem, in the first problem, we have 1 OH.
Right. Because here our nucleophile is the carbanion. Ring open, form the OH.
Okay.
Here our nucleophile is water. That's where the second OH comes from.
Okay. So that second part in the first problem isn't adding any more.
Right.
Okay.
We add
That's us.
the carbanion here, ring open. The acid, we simply put the proton on.
Okay.
All right, let's do a very sophisticated problem based on the stereochemistry of our addition. All right, are you ready? If we take this transalkene, we can react it to make 2 diols. Now we know 2 ways to make 1,2-diols, don't we? A manganate is going to give us a cis 1,2-diol. The epoxide, followed by ring opening, will give us a trans 1,2-diol. One of these was made with epoxide, trans ring opening, and the other one was made with permanganate. What you have to do is figure out which is which. Now let's go back to stereochemistry. As we look at, say, this structure here, we have used wedges to show us that these groups are coming towards us, and therefore these groups are going away. Everyone see that? Everyone remember that? Well, there's a simpler way to show that we did way back in chapter 5, and that is to use a sawhorse projection. Remember, in a sawhorse, we use this, for example, as our front carbon, and that's our back carbon. We're going to draw a sawhorse with this going up, this going up, this down. Again, this would be up, up, and down. Go ahead and draw a sawhorse for each of these. Don't remember what a sawhorse looks like?
We do. Dr. Young, I thought that the line was in the plane. I thought only when it had like little lines, that
Well,
was pointing back.
But if we define our stereochemistry with these guys coming towards us, this must be going back. This is actually a modified version of what's called a Fisher projection. In a Fisher projection, you don't have to use wedges at all. You just understand that anything horizontal is coming towards you. But Fisher isn't covered in the new McMurry until like chapter 26 or so. All right, in our sawhorse projection, this is going to be our front carbon. Going to have a phenyl going up, hydrogen going up, hydroxyl down. Phenyl group up, hydrogen up, hydroxyl down. Go back and look. Phenyl up, hydrogen up, hydroxyl down. Our back carbon, hydrogen up, hydroxyl up, methyl down. Hydrogen up, oxygen up, methyl down. Our second guy here, we have phenyl down, hydroxyl and hydrogen up. Phenyl down, hydroxyl, hydrogen up. Back carbon, methyl down, hydrogen, hydroxyl up. So, there are our two sawhorse projections. Now our second step, once we make a sawhorse, we want to take and rotate so that the phenyl and the methyl are on opposite sides of each other. Why do we do that? Because look up here, here's our double bond we started with. It's trans, phenyl and the methyl on opposite sides. So we want to take this and rotate so that phenyl and methyl are opposite from each other. Now, if we leave this guy still, then all we have to do is rotate this carbon, this bond here, so that the methyl group is now here, opposite and parallel to this bond. Look at what we've done. We moved the methyl up, moved the hydroxyl up, moved the hydrogen down. Methyl up, hydroxyl up, hydrogen down. These two bonds are now parallel, just like they are here. Now you look at your hydroxyl groups. What is the relationship of our two hydroxyl groups? They're opposite each other, aren't they? That means the hydroxyl groups are trans. If the hydroxyl groups are trans, we made this by making an epoxide and then ring opening. Isn't that clever? All right, let's deal with this guy. Let's arrange it so that the phenyl and the methyl look exactly the same as they did here. Okay, just to make it easy. That means we're going to have to rotate them both. Going to have to spin this so the phenyl comes up, like it is here. That means the hydrogen will come down, and hydroxyl group will be over here. Phenyl comes up, hydroxyl group moves over, hydrogen down. Phenyl up, hydrogen down, hydroxyl over. looks just like this one now. We have to do the same thing we did over here with our methyl. Have to rotate it a bit so it's up, parallel to this bond. That's going to move the hydroxyl up, move the hydrogen down. Methyl goes up, hydroxyl group up, hydrogen down. Methyl up, and down. So now our backbones are the same, aren't they? Look at the hydroxyl groups. If this bond here in the middle is our plane, like it was here, here on this ring plane, or not ring plane, but this plane, this bond, we had hydroxyl up, hydroxyl down. Here we have hydroxyl up and hydroxyl up. They are cis, which means that we made this with permanganate. Now this is a fairly sophisticated problem. This was actually on the final exam from the last time I taught Organic 2 at UIC. Any questions? All right, let's talk about fun things ethers do. Ethers can be synthesized into what are called crown ethers. Now they get their name because if you look at this as a model, the oxygens and the CH2s around form a up and down sort of thing. If you look at it, it kind of looks like a crown. Okay? Crown ethers. When you are naming a crown ether, the first number here, in brackets, is the total number of atoms in the ring. So this is 12. Crown means it's this basic structure, and 4 is the number of oxygens. So 12 crown 4, 15 crown 5, 18 crown 6, 21 crown 7, 24 crown 8. All right, we're not going to do crown nomenclature, but this is what it's called. This is how you do it. Now, the neat thing about crown ethers is that they have this hole in the middle, right? If you have a hole in the middle, what do? You can put things in it. Turns out that the hole in these top 3 fit the ions lithium, sodium, and potassium perfectly. Lithium, the smallest, will bind in the middle. Sodium is larger, and potassium is the largest. Now this is actually kind of neat because if you want to do a synthesis or something and you need an inorganic something or other dissolved in a nonpolar solvent, how in the world would you get the potassium salt in? Very simply, add a little 18 crown 6. It takes the potassium, wraps its arms around it, and makes it soluble in nonpolar solvents. Let's look at 18 crown 6. This is what it looks like. Again, there are 18 atoms, there are 6 oxygens, and it's a crown. Once again, potassium ion fits perfectly in this little hole. This is what it would look like in a stick model. Again, we have all of our oxygens pointing in the middle. Now remember, the oxygens are Lewis bases, aren't they? They have these electron pairs sticking out, and because of that, they can interact with this metal ion. So when we stick the potassium in the middle, it's actually chelated by all of these oxygens. If you look at this as a space filling model, it's even cuter. Here you can kind of see why it's called crown. We have up and down, so up, 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 down, down, down. Here's our big hydrocarbon thing around it, and we've totally surrounded our potassium. Kind of a neat thing. Now, organic chemists weren't the first to think this up. Ever heard of valinomycin? Some of you are called fair professionals, I'm sure you have. Valinomycin looks like this. It's secreted by Saccharomyces, and it's an antibiotic. It's actually a fairly novel, interesting antibiotic. If you look at the structure here, this is alternating amide and ester bonds. Amide bond, this guy here, carbonyl NH, attached to stuff. Next to it is the ester, carbonyl oxygen. When you take and you do a 3D model of valinomycin, stick a potassium in the middle, this is what you get. These are the ester carbonyls, these guys, and they're all pointing in. The amide carbonyls are these guys, and they're all pointing out. We have 8 carbonyls bonding with the potassium, and that, again, solubilizes the potassium, which binds in the middle of this cyclic structure. Why is this an antibiotic? Well, remember I said you could take 18 crown 6 potassium and dissolve it in a nonpolar thing, right? Well, bacteria exist because they can maintain sodium on one side, potassium on the other, etc., just like we do, frankly. But if you then take 18 or valinomycin, it can chelate potassium from the outside, move it to the inside. The bug can't deal with that, and it's dead. Kind of a cute thing. Any questions? All right. Let's do a problem here. We talked about 18 crown 6. Predict for me its proton and C13 NMR. Remember from our last exam, the real question here is, how many unique carbons do we have in this molecule?
1.
That's it. Because this is magnetically equivalent to this guy. Therefore, the C13 NMR looks like this. 1 peak. If we had proton coupling, this is a CH2, so it would be a triplet.
Isn't it like interesting or something where you miscommunicate one little thing and it can change your test points by a letter grade?
Well, Yeah, I suppose that is interesting. Simple exercise in symmetry. This is a carbon next to an oxygen and carbon. This is a carbon next to an oxygen and a carbon. The same C13 chemical shift.
Which concludes you cannot judge a person by his test.
All right, how about the proton NMR? All these carbons are next to an oxygen, aren't they? So that means they're going to be shifted down and next to something electronegative. So it's going to be 3 to 4-ish, right? In there somewhere. Are they going to be coupled to each other? We have two CH2s. Are we going to get
Yes.
triplets? Except, how would it be a triplet? Because they would have exactly the same chemical shift, wouldn't they? It's a singlet. The rule to remember is if the carbons have, the hydrogens have exactly the same chemical shift, then they do not couple. Now this is a little sophisticated, a little more sophisticated than we've done in the past. But again, if they have exactly the same chemical shift, they are always magnetically equivalent. And if they're magnetically equivalent, they don't couple. Any questions? All right, let's look at sulfides very quickly. Sulfides are simply the sulfur equivalent of an ether. Remember, sulfur is right below oxygen. We talked about thiols. Thiols and alcohols had very similar reactivity. Sulfur is a much better nucleophile. Frankly, in terms of ethers, sulfides win because they're much more interesting. Sulfide is going to be a sulfur with alkyl or aryl groups on either side. We would name them simply by calling it a sulfide. If we have somebody else as our parent, we can name it as an alkyl thiol. So this is methyl thiol, that's this guy here, this guy here. We're not really going to do sulfide nomenclature on exams. This is a nice simple example: ethyl, methyl sulfide, methyl phenyl sulfide. Now, how do you make ethers? You make them by the Williamson synthesis, right? How do you make sulfides? Simplest way is by the sulfur equivalent of the Williamson synthesis. Sulfur anion, very good nucleophile, much better than oxygen. Simple SN2 reaction, and we get methyl phenyl ether. When we talked about electrophilic aromatic substitution, we pointed out that the thiolate anion, because it's such a good nucleophile, is actually very good at doing a nucleophilic aromatic substitution. Here we wind up with the 1, 2, 3, 4, so that's a butyl, 2,4 dinitrophenyl ether. Thiol. Any questions? The one thing that you can do with sulfides that's really interesting actually is the sulfur, even though it's bound up now with two covalent bonds, is still nucleophilic enough that you can actually alkylate this. If you take a simple sulfide in the presence of something like bromomethane, you can make a stable sulfonium salt. If this was an oxygen, it would be very unstable. Its lifetime in solution would be like 10 to the minus 9 seconds. Very unstable. If this is the sulfur, it's a very stable compound. Biochemically, there is a sulfonium compound that exists. It's called S-adenosyl methionine. If you look at that, this is adenosine over here. This would be the amino acid methionine, and we've made a sulfonium salt as our linkage here. Biochemically, this methyl group can be donated. In other words, this is a methylating agent, biochemical methylating agent. When you do when you take DNA and you sequester parts of a gene, the way that you shut off a particular set of genes is by methylating. So when a cell differentiates, it goes from a stem cell to a nose. The nose cells have been methylated by S-adenosyl methionine. Very key part in cell differentiation. Very simple reaction. Again, the way it happens is just the opposite of this, really. Nucleophile attacks, and you go back to the sulfide. Any questions? One other thing that you can do with sulfides, once again because the sulfur has these lone pairs but can still react with them, is you can oxidize them. If you just take a sulfide in the presence of peroxide, you make what's known as a sulfoxide. You can take a sulfoxide in the presence of a peracid and make a sulfone. Sulfoxides are very interesting compounds. Dimethyl sulfoxide is used as a solvent. We talked about this when we did SN2 reactions. It's one of our magic solvents. It's a magic solvent because it is soluble in nonpolar stuff, but because this is a plus minus, it's polar. So it promotes things like SN2 reactions very, very nicely. You may know DMSO. That's dimethyl sulfoxide. For a while, it was considered trendy to take DMSO and like smear it on arthritic joints. What happens is DMSO, because it's very soluble in lipids, so nonpolar things, is absorbed very, very rapidly through your skin, very rapidly. Once it gets in there, it's reduced to dimethyl sulfide, which stinks like mad, so you smell, but it does have an effect of easing the pain in an arthritic joint. Problem with it is that DMSO is such a darn good solvent, an amazing solvent, that if you happen to have anything on your skin that's being held out by the skin, which that's the skin's job, and you smather DMSO on it, it's just going to take it all and move it inside, straight into your bloodstream, which can be a very bad thing. So it's very dangerous unless you're using ultra pure, and you make sure that the site of application is very, very clean. Any questions?
So like years ago, they had this thing called Tiger Balm, is that what had it in there?
It could have. I mean, there were lots.
People were doing it back in the 80s.
Yeah, there were lots of things. I mean, there were people that would take drugs, for example, put them in DMSO, smear it on their body. You get this instant. The only real downside of that is you smell like dimethyl sulfide, which is like skunk. And you smell that way for days afterwards.
Oh, yeah,
So,
no, I had a couple
Sure,
of
it's worth
coaches
it, you
using
can't
that.
walk.
Well, I had a lot of coaches using that at the time.
So you don't want to do that. All right, let's finish this all up with a couple quick synthesis problems. Oh, no, we have one more reaction. This is actually useful. If we take a carbonyl compound, and we'll learn a little bit more about this when we do the next chapter, which is carbonyl compounds. You can react that with a 1,2-dithiol. And you can make what's called a thioketal. So here we have the sulfur equivalent of ethylene glycol. Here we have a carbonyl, and we make this stuff. Now this is a very good protecting agent. Remember we talked about protecting agents, except this goes one step further. Once we make the 1,1-disulfide here, so 1,1-disulfide, you can reduce this with Raney nickel. Raney nickel is just a simple reducing agent. It's hydrogen and finely divided nickel. This goes smoothly to get rid of your carbonyl and give you just the alkane. So it's a neat way to get rid of the carbonyl. It also makes it very unreactive if you were doing like a Grignard or something like that. But again, we'll talk about ketals in the next chapter. All right, now let's do a couple synthesis. These are going to be 2 or 3 steps. So they're getting to be a little more sophisticated. What we want to do here is start with benzyl bromide. And we want to make this ether. Okay? Remember, when you do a synthesis, you're going to be thinking backwards. So you always start with your product. And you say to yourself, what is it? Once you identify the functional group, you say, how many ways do I know how to make it? Choose a way. What reaction would yield this? If you take that intermediate and start working back to your starting material. So let's do this. It's an ether, right? How do we make simple ethers? Simplest is by the Williamson synthesis, the SN2 reaction. So we could do this if we had an alcohol and an alkyl halide. That's the simplest way to make an ether. Okay. The alkyl halide, since we have a methyl group dangling down here, it seems to me that this is a good candidate for the alkyl halide part. So something like methyl bromide. That means that everything up top here, from the oxygen up, was the alcohol. So what you do is you simply split this. This was an OH, or an O minus, and this was bromomethane. Going to split here. This was our alkyl halide. All of this was the alcohol. So, the reaction looked like this. Start off with the alcohol, That's all of this. Going to use sodium amide or something like that to make the alkoxide, because we need the alkoxide, remember. And then we're going to dump in, well, here I used methyl iodide. Again, methyl bromide would work just as well.
So all the alcohols including the ring or excluding the ring?
Everything from the oxygen up is part of the alcohol. This is what the alcohol would look like. Now, you could have split on the other side, couldn't you? Used methoxide and have a leaving group here. That's why synthesis is so much fun, because you get to make choices. All right, now our new problem is this one. We have to make this alcohol starting from benzyl bromide. So we say to ourselves, it's an alcohol. It's a secondary alcohol, isn't it? Think back to last chapter. How many ways do I know to make secondary alcohols? The simplest is an aldehyde and a Grignard, isn't it? Grignard reagent and an aldehyde. All right, now you're allowed to peek at your starting material. Your starting material has a benzene ring and a CH2, doesn't it? We can make a Grignard out of this, can't we? So down here, the benzene ring and this CH2 were your starting material. This guy down here, this half, was your aldehyde. Let's color them. This is our Grignard. It's these carbons. This was the aldehyde, and this is the bond we just made. Draw the structure of the appropriate aldehyde. The aldehyde had two carbons, right? Methyl group, and this used to be the carbonyl. It's an aldehyde, so the carbonyl is attached to a hydrogen. Convert this to the Grignard, react it with ethanal, or acetaldehyde, as it's commonly known. These are the two carbons down here. This converts to the OH. And so our full synthesis. Going forward now, you start with benzyl bromide, make the Grignard, react it with acetaldehyde to make the alcohol. Take the alcohol, treat it with a strong base to make the alkoxide, dump in an alkyl halide to make the ether. That is organic synthesis. Any questions? Now that we can all do it, let's do it again. Starting off with 2-phenylethanol, and we're making styrene oxide. Remember, you're only allowed to peek at your starting material. You start working with the epoxide. We see here that in our starting material, we have a benzene ring that shows up here. We have 2 carbons. They're going to be those 2, aren't they? All right, so we're making an epoxide. How do we know to make epoxides? 2 ways, only 2 ways. We can do per-acid oxidation, or we can do halohydrin and an internal SN2. Let's go ahead and do it the halohydrin way. If this came from a halohydrin, that means that 1 carbon had the OH group and 1 carbon had a halogen. So if we had this molecule, we could treat it with a strong base, make the alkoxide, kick out the bromine, and make the epoxide. That'll work. Now, how do you make a halohydrin? Think back to chapter 6. We make a halohydrin with an alkene and HOBr. What's the alkene going to look like? Well, we're going to add HOBr, so this was a double bond, right? Two ways that we used to make HOBr. One is actually bromine and water, or we can use N-bromosuccinimide and water, same thing. Now, we have to figure out some way to get from our alcohol to the alkene. Remember, we just did a chapter on alcohols, didn't we? And there was one very nice reaction for making alkenes. It was an E2 elimination, wasn't it? We did that by taking the alcohol and reacting it with phosphorus oxychloride, POCl3. We made a chlorophosphate ester, which then underwent a really nice E2 elimination. Last chapter. So, to go from here to here, simply take POCl3 and pyridine, and we make the alkene. E2 elimination. Now, there's a simpler way to do all of this, isn't there? If we worked our way down, or did this elimination and made styrene right here, how can we make this directly? Again, we only know 2 ways to make epoxides. One is halohydrin, and the other is peracid. So we took the peracid here, or this plus peracid, we would get this as our reactant going directly to here. I also put in a second set of reaction conditions you could use to do the elimination. Again, this is paratoluene sulfonyl chloride, make the tosylate here, and then do the E2 elimination. Both of those work nicely. I think the POCl3 is probably better. By the time we finish this course, syntheses like this will be so simple. Any questions? All right, I promised that we would now go over the exam. We'll do this as quickly as we can. If you want to take just a 5-minute break, we can do that while I set up. But please keep it 5 minutes.